Welcome to this presentation on initial value and final value theorems. The outline is as follows. We will present the initial value theorem, final value theorem. We will give examples of final value theorem, and then we will also point out the importance of final value theorem. Let us first consider the initial value theorem for causal signals. Let U be a causal sequence. Here is the result. The value taken at time instant 0 is nothing but applying z equals infinity in U of z if the limit exists. Let us see the proof. This is the definition of Z transform. Because U is given as causal, we need to evaluate this sum from k equals 0 only. So we write it as k equals 0 to infinity of the same sum, which we write down in expanded form. K equals 0, you get U of 0. For k equals 1, you get this, k equals 2, and so on. Now, this will go all the way up to infinity. Let us take the limit. What do? We take the limit as z going to infinity, this limit. The left hand side is limit z going to infinity of U of z. On the right hand side, when you substitute z equals infinity, this term becomes 0, this term becomes 0. In fact, all the terms become 0 except U of 0. So we get this result. This is known as the initial value theorem. Initial value is obtained by letting z go to infinity in the Z transform. We will see the final value theorem for causal signals. Under the conditions uz converges for all z greater than 1 and all poles of uz into 1 minus z inverse are inside unit circle. We get this important result. Limit k going to infinity of uk equals limit z going to 1 of 1 minus z inverse into u of z. So on the right hand side, we are multiplying uz with this factor. This helps because it can handle one pole of u at z equals 1. If there is a pole like that, then these two will cancel each other. This is useful when we work with step responses. Let us see the proof of final value theorem. I claim that this expression is identical. All that I have done is to add this u of minus 1. Why is this? Because it is given that u is causal. So we have for all negative arguments u 0. So in particular here u of minus 1 is 0. So we see that we have not modified anything by adding this u of minus 1. I do the same thing for u of 1. What do? I subtract and add u of 0. So I am not doing anything with respect to 0. I have u of 1. I have this extra term which is 0. I keep on doing this all the way up to u of k. So everything goes away except u of k. So this is an equality, u of k equals u of k. Now I group two terms at a time, and so the first one will have u of minus 1 and u of 0. The next one will have u of 0 and u of 1, and so on, all the way up to k minus 1 and k. And we call this as delta of u0, this as delta u1, and so on. We will generalize this relationship as follows. Delta of un is un minus 1. So this is delta u0, delta u1, next one is delta u2, and so on, all the way up to delta u of k. Okay. So limit k going to infinity of uk is nothing but delta u0, delta u1, all the way up to delta u of k. Alright, so I get this expression from the previous page and I can add some more terms. What happens before this? Negative arguments, delta u of minus 1, delta u of minus 2 and so on, they are all 0 because u is causal. The value of u is 0 and so the differences are also 0 for k less than 0. So using all this, I can write this as this sum as an infinite sum with argument k going from minus infinity to plus infinity. Okay. Now what we do is we will apply the meaning of delta of u of k, which is nothing but uk minus u of k minus 1. Everything else is the same. We got this z power minus k, this sum we got, this limit also we got identical. Okay. Now what we will do is we will apply the linearity theorem. So in other words, we will multiply and take the z transform separately. So we get u of z, and for this remember we have to use the shifting property. As a matter of fact, there is one time sample delay, so we get z power minus 1 into u of z, and I can group this u of z, I can pull it out, so I get this. So here is the final value theorem which we have proved. So limit k going to infinity of u of k is given as this. It is important to remember that this is true only for causal signals. We will give an example. Using the final value theorem, find the steady state value of this and verify. Steady state value means as n goes to infinity, what is the value? Recall the final value theorem. Let us recall the meaning of this. Nothing but z transform. The moment I put this left right arrow, I mean on one side you have the time domain expression, on the right hand side it is the z transform. We have already seen this. In fact, it is very easy for you to verify that this term will give rise to this and this will give rise to the second expression. Now limit n going to infinity of LHS, LHS denotes left hand side, let us substitute n equals infinity, then this will become 0, then we have minus 0.5. The second term gives rise to minus 0.5. What about the right hand side? So we will apply this property, we will take z going to 1 of 1 minus z inverse multiplying this whole thing, okay, of RHS which denotes right hand side. Now let me just multiply directly. When I multiply this term by 1 minus z inverse and let z equals 1, this term will become 0, so this whole thing will become 0. Whereas this 1 minus z inverse, when it multiplies this, so we get, it will cancel this term in the denominator, so we get minus 0.5. So we have verified that the left hand side, when I take the limit, I get minus 0.5. When I apply this on the right hand side with uz substituted as this, I get minus 0.5. So we have verified this for this particular expression. I will next give an example that demonstrates that one should not apply final value theorem blindly. I have this question, is it possible to use the final value theorem on 2 power n into 1 of n? Here is the time domain sequence, here is the z transform. Remember, we need to use the region of convergence, because when you take z transform, you sum up infinite number of terms. So you have to make sure that you choose the values of z properly and that sum converges. Since the right hand side is valid only for z greater than 2, this theorem cannot even be applied. So that is about the right hand side. What about the left hand side? In the left hand side also there is a pole that lies outside the unit circle. In the left hand side also you have a term 2 power n which blows up as n goes to infinity. In fact, this too appears as the pole here. So, the left hand side also does not converge. So, one should not blindly substitute, one should check the validity before using. So, we cannot by trick make unbounded sequences bounded. It is important. Let me emphasize again, on the left hand side you have 2 power n as n goes to infinity, this term blows up, this results as a pole here, it has a pole at z equals 2. So, this is applicable only when absolute z is greater than 1, but the final value theorem says that you have to apply z equals 1. If you do not worry about this condition, you will blindly apply z equals 1, then it will be 1 over minus 1. Some people report this as value having minus 1. That is totally incorrect because you cannot even apply this result. Final value theorem is extremely important. In control applications, we would want the closed loop system to be stable. That is, we would want, let us say, the output of the system to be bounded as t goes to infinity or the sampling instant n goes to infinity. We would want to quickly check this fact. The controller will be in Z transform. Can we quickly check whether the controller is acceptable directly in Z transform without having to invert? Because of this, we say that the final value theorem is very useful. So, we will use this fact very often in this course. With this, we come to the end of this presentation. Thanks for joining.